Hello. This is Rising Tide by James Sinclair. It is the first puzzle of his Artisanal Sudoku 100, volume 109. Yeah, I've done this like 3 other times before this, and the puzzles are really good, so you should check it out. Pretty excited to solve the puzzles for this week as well, so yeah, I'll be doing it. I actually got a shout out by, I was shouted out by James on his page, which, yay, that's so cool. Yeah, it's there. I'll link it in the description of this video, but yeah, I was gonna say that. Before we get distracted, let's go to the rules of the puzzle. Normal Sudoku rules apply, so place the digits 1 to 9 in every row, every column, and every 3x3 box. Can you just show their sums? So these 3 digits, for example, sum to this small number here, 15. These 3 digits sum to 23. These 3 digits sum to 7. On thermometers, digits have to increase from the bulb. So you have this long thermometer here going from the bulb to the tip. And digits have to be increasing, so you know, this is this is an example of a valid thermometer. And yeah, it doesn't matter how it increases. Everything that matters is that every digit is greater than the previous one on the thermometer. Right, so those are all the rules. A very minimal Sudoku this time. So with that, let us get started. James Sinclair always makes super cool minimal Sudokus. Like all of his puzzles use very little rules, so that's great. I think we start off with these 7 length thermals here, because if I wanted to good lift it, I can. And good lifting is just the act of placing in all possible digits in each cell, because we know that we know that the minimum digits on here are 1, 2, 3, 4, 5, 6, 7 if you increase by 1 every single time. But the maximum here would be 3 to 9 if you pick the highest possible digit. If you start off 9 here and decrease by 1 each time, you get the highest possible. And then you always have a single or 2 degrees of freedom between that. So we're starting off with those there. These are like, this is generally, I don't know, generally not very advised, but I'm doing it for my own convenience. We can also work on these little clues here. This clue is actually quite large. It is 23, and the only way to make 23 in 3 cells is 6, 8, and 9. Now the one way to think about how this is possible is if you consider the maximum digits you can put in 3 cells, they are 7, 8, and 9. If you want to make, these are 24, so if you want to make 1 less to make it 23, you have to decrease one of these digits by 1, and exactly 1 digit decreases by 1. You can't do that to 9 or 8 because they would result in a repeated digit. So you can only do that to 7, which must turn into 6, giving you 6, 8, and 9. And 7 can also be only made with 1, 2, and 4. And you can probably try and figure out how that works out yourself. But that does give us digits, because this one now can't be 2 or 4, so it has to be 3. That now can't be 3 or 4, so that's 5. And so I guess that's no longer, well, this must be greater than 5, so that must be 6, which means everything is pushed up to the maximum. And this can't be 3. We can also do the same here with 6, 8, and 9. This can't be 6 or 8, so that's 7. This can't be 6 or 7, so that's 5. And now 5 pushes everything down to our minimum. This can no longer be 7. And I guess interestingly, 6, 8, and 9 form a triple here. 1, 2, and 4 form a triple here. Actually, this 1 resolves this. This has to be 2. None of those cells are 2, so 2 goes there. This 9 makes that an 8. None of those cells are 8, so 8 goes there. Great. Starting off nice and easy. Oh, this is meant to be like one of the easier puzzles, so that does make sense. Now, 2 in this box, because of those 2s, can't be there. This also can't be 2, because there aren't 3 digits that are below 2, so 2 has to be there. And so now 2 in this box can only be here. I think we can do the same for the 8s. Yeah, this is a very rotationally symmetrical puzzle. 8s come in those cells by these 8s over here, and 8 can't be there because there are no 3 digits that are greater than 8. You only have 9, so 8 must be there, which means 8 is here in this box. Can I do something similar up here, maybe? Not entirely. No, not really. Say 5s might be interesting. I realized that this puzzle might be very it might have this like X windmill property where every 2 rotationally symmetric cells in the grid sum to 10. Obviously I can't prove that, but that's my guess, in which case I could have put a 5 here, but I'm not gonna do that because that's not how this puzzle should be solved. Those digits actually do form a triple. Those are 1, 6, and 7. No, those are not 1, 6, 7. What am I saying? 6, 7, and 9. That cell can be 7. Now those cells are 1, 3, and 4. That can be 3. Okay, so this is where difficulty starts increasing, I guess. I can say 8 is one of those cells because 8 here sees those cells, and none of these cells can be 8 because because the 8 doesn't have 2 cells or more that's larger than it. So 8 must be one of those cells, which means now in this box we can actually place an 8. 8 here and here sees those cells. Whatever the 8 is here would see those cells, so 8 must go there. Great. Now what? 8 is in one of those cells. These cells here. And I guess here they're in those 2 cells, which makes sense. But no need to mark that right now. We can do the same for 2s, I think, because it's basically symmetrical. Yeah, 2s can't be in those cells, can't be those cells because there are no 2 digits less than 2. So 2 is in one of those cells. Therefore, in this box, 2 must be here, which means 2 is in one of those cells. And in one of those cells, of course. That's cool. Now what? Okay, let's figure out where 1 goes in this. Yeah, 1 sees those cells. Wherever the 1 is here would see those cells. 1 can't be here because there are no digits less than 1. So 1 actually is one of those cells which pairs up with the 8 to form a 1-8 pair. And this also forms a sort of X-wing here. But I guess it's more... Yeah, it forms an X-wing to say 1 is one of those cells. But a more logical way to think about that, or not more logical, but a cleaner way to think about that is in this column where there's 1 go, 1 can't be in any of those cells, and because wherever the 1 is here would make those cells not 1, 1 can only be one of those cells. Cool, and I assume we can do that from to 9 as well. Yeah, 9 can't be in those cells, wherever 9 is would see those cells, that can't be 9. So 9 is one of those cells with a 2, forming a 2-9 pair. 9 has to be one of those cells by equivalent logic. 9 can't be there or there. So that's how it works. I could probably also explain how X-wings work, you know, just quickly. Like there is 1 9 in one of those cells, there is 1 9 in one of those cells. Because of these 2 columns, there are 2 9s exactly in this set, and therefore, because there's 1 9 here and 1 9 here, those are the only 9s in these 2 columns. Nowhere else in the grid nowhere else in these 2 columns, sorry, can there ever be a 9. So 9 is not in those cells, meaning they have to be there. So that's how X-wings work, which become quite versatile. I don't know how exactly useful they become in after a while, but yeah. Alright, so 6 in this box now does help us because 6 can't be in those cells, 6 sees those cells there, so 6 goes there. We can put a 4 here, I think by equivalence. Yeah, 4 in that cell and that cell would see all those cells, so 4 goes there. This helps because none of those cells are 4, placing a 4 there. This 6 sees those cells, placing a 6 there. Great. That probably wouldn't help with the middle column though. Okay, what else do we have? Well, I know that cell now can't be a 1. Yeah, and I guess a way to say that is in this box where there's 1 go, 1 will have to go in one of those cells because it can't be any of those cells. And therefore, because wherever the 1 is would see that cell is not 1, that's 4, that's 1. And another way to think about it, which I'll demonstrate here, is that if this cell was a 9, for example, then none of those cells can be 9. But none of those cells can be 9 either because there is no digit greater than 9. So this cell can't be 9. That's 6, that's 9. It's really the same type of logic. But yeah, I'm just yapping. Which means we know 9 goes in one of those cells. Therefore, because of these 9s, they would see those cells. 9 is one of those cells. And I guess because of this, we know about the X-wing trick. 9 must be one of those cells, because of this 9 seeing that cell there. We also know by this X-wing trick over here that 9 has to be, well, it's not there, and this 9 sees that cell, so 9 is one of those cells, which forms yet another X-wing, but I think at this point it is not quite useful anymore. We can do the same for 1s. 1s here, with this 1, see all those cells, so 1 goes there, and then we can place a 1 in one of those cells because of these ones. Then this one and this one here sees the middle cells, that sees that, so 1 is one of those cells. So very, very similar logic. We need, let's look at some columns, shall we? This column maybe? Those cells have 1, 6, 7, 8 in them. Right, and this one, wait, yes, this one does help, because this can't be 1 or 8, so in this must be 6 or 7. But it can't be 7 either, because if it was 7, you'd have to increase immediately to 9, so 7 would have to be 8, 9 here, which doesn't work. As you can see, 8 here is seen by that 8, it's also seen by wherever the 8 is here. So that can't be 7, it must be 6. And therefore, because those digits have to be bigger than 6 but not 8, they have to be 7 and 9, which have to be increasing like so. That resolves this 7-9 pair here. Those digits are then 5 and 3. This 1-3 pair here means that can't be 3, so that's 5. That's 3. And I think, oh, 3 in the corner. Nice. That is a 7. So that's great. We can probably do the same on the opposite side as well. Those digits are 2, 3, 4, and 9. This can't be 2 or 9, it's 3 and 4. And by the same logic, this can't be 3, because that will put a 2 in one of those cells, and that breaks. So this has to be 4. This now has to be less than 4, but can't be 2, so it has to be 1 and 3 in this order. Resolving this 1-3 pair. Those digits have to be 5 and 7, which we can resolve. That's 5, that's 7. This 1-3 pair now looks at, this 1. The 3 has nothing to do with this, but this 1 sees that cell, so that's 8. That's 1. Okay, those digits are 3, 6, and they're just 3 and 6. What am I saying? And then those digits are 4, 5, and 9. So 9 is not there. That digit is a 3. Oh, that resolves this 3, 6 pair here, so 6 there, 3 there. Those digits are 4 and 7. This has to be 4 because of the 7 here. Those digits are 1, 5, and 6, I believe. That cell can be 1. That's great. Okay. Now what? I mean, those digits we know are just 1 and 2. Wait, no, they're not. 1 and 1 and 5. Sorry, 1 and 5, and the same can be said here. This has to be 5 and 9. Actually, these digits are part of a triple, which are 2, 9, and 3. So 2, 3, 9 here. That cannot be 2. This one, oh wait, we got oh, this one, right, this 9 here sees that cell, so that's 2. That's 9. That makes this a 3, so that's 2. This one can probably also resolve. Those are 7 and 8, which we can indeed resolve. 7, 8 here. Those digits are therefore 6 and 9. Nice. And those digits are 1 and I guess 4. 1 and 4, yep. This 8 means that's not 8, which forces 8 here. This 2 means that's not 2, forcing a 2 here. And this 15kh now tells us a 5 goes there. Do I need that 5 though? I mean, yeah, I guess that this was a 5 because it was a rotationally symmetrical puzzle. I think I do need the 5 to solve this puzzle though, so I'm just going to put it in. We know it's a 5 because of the 15kh. This resolves this 1, 5. That resolves this 5, 9. This one resolves this 1, 4. That resolves, this 9 resolves this 6, 9. So now we have, well, those are no longer 5s, which doesn't give us much. But we can use the rest of the puzzle to solve. This is 1, 3, and 6. 3 come in those cells by those 3s, so 3 goes there. 6 come in there, so that's 1. 6, that resolves this, that says 1. This is not 1. Alright, fair enough. Those are 9, 7, and 4. 7 coming there, so 7 goes there. This is a 9-4 pair, which we can resolve. This is no longer 4, so that's 9. That is not 9, which is resolvable. This 4 here resolves this 4-5 pair, and this 6 here resolves this 5-6 pair, solving the puzzle in 13 minutes and 42 seconds. Cool puzzle. Yeah. I liked all the steps here. It is a symmetrical puzzle. So if you're speed solving, you could kind of infer that and say that that's a 5. Yeah, and a cool thing to think about when doing these puzzles, right, is that you can notice that those cells sum to 30, which is 3 times of 10, which makes sense because you have 3 sets here of digits that sum to 10. But I guess you can't really prove that it's a rotationally symmetrical puzzle until you actually solve it. So yeah, that was a cool puzzle. Hope you enjoyed this video. I'll see you next time. Bye bye. Hello, this is #Renban by Full Deck and missing a few cards. You might notice that this puzzle is a little out of place. Not for the wrong reasons. Because this video is actually for Artisanal Sudoku by James Sinclair. It turns out that Full Deck and missing a few cards actually submitted a puzzle, which was featured for this week, so that is really cool. Yeah. This puzzle should be as per normal though, besides the who made it. So yeah, I reckon I'll have some fun with this. So let's look at the rules. Normal Sudoku rules apply. Digits 1 to 9 must be placed in every row, every column, and every 3x3 box. Digits in cages cannot repeat and must sum to the total given in the upper left corner of the cage. So you have a lot of cages here, actually a lot of cages. They cannot repeat. So for example, those digits cannot both be 3 because they're in the same cage. Even though they would work by regular Sudoku, they cannot both be the same digit. And must sum to the total given in the upper left corner of the cage. So those 3 digits, for example, sum to 14. Those 3 digits, for example, sum to 20, and the same occurs for all cages. Digits along a pink Renban line form a non-repeating set of consecutive digits in an order to be determined by the solver. So what that means is that here you have 5 cells connected by a pink Renban line. They have to contain 5 consecutive digits in any order. So 5 consecutive digits could mean 4, 5, 6, 7, 8. This is a valid line. And it doesn't have to be in a specific order, it just has to contain those lines. Sorry, those digits. And the same goes for every line here. Yeah, so that's it. With that, let us begin solving. So I actually don't really see what we could do here. I know this is 8 though, must have a 1 in it, because the minimum you can make without a 1 is 2, 3, and 4, which sums to 9, which isn't correct, so it has to have a 1 in it somewhere. And 1 can't be there, can it? Because if 1 was there, the remaining digits on the line have to be 2, 3, 4, and 5 to make your 5 consecutive digits. This means that those digits are then at least 6 and 7, which already sums to 14 if I can do my math right. So that can't be 1. So we have some progress, but not a lot. I don't actually know where else I can do stuff. I mean, this 8 also does something similar, where 1 is one of those cells. And, well, I don't know where else I can do something similar, because all of those other cages are very average, actually. Like, 20 is the biggest one I can find, but even that doesn't give me a lot of freedom. Because you don't need to have a 9 in that, even. So yeah, interesting start. Maybe something interesting about the hashtag here in the middle is that, well, the hashtag must have, well, these 4 lines must have a 9 in them somewhere. And same for 1, it must have a 1 and a 9 in them somewhere. I mean, they obviously can't be on the same line, because the line would then have to be 9 cells long. But wherever 9 goes has to be followed by 8 and 7 at the very least. Right? I mean, not specifically in order, correct? Because 9 here could have 8 and 7 there, and then 6 and 5 here. But wherever the 9 goes, that does something. Wherever the 1 goes, it does something as well. I'm not quite sure how that is useful. The 25 also not useful because 25, actually 5 digits can sum from anything, sum up to anything from 15 to 35. So this is again stunningly average. Maybe we could do some math with this line then, because if this is a 1, that could say something. Because this could be a 5 at maximum, right? But this means that this could actually be a line from 9 to 5 or 5 to 9. So this again isn't actually restricted by the 8 gauge, because this could be a 5 with this being you know, a lot of things. So if this was a 1, then this total sums to 26 plus this sums to 27. And we know a box has the digits 1 to 9, which sum to 45. Now this is 27 if this was a 1. Those digits would have to sum to 45 minus 27, which is actually 18, which is impossible. Huh, so this just can't be a 1. Well, would you look at that? Yeah, 18 isn't possible because the maximum 2 digits can be is 19, which if you use 8 and 9. And actually, I can tell you that this probably does help, because those sum to 26. Those would have to therefore sum to 19 in 3 cells. So they have to be relatively high, right? Yeah, they do have to be relatively high. Okay. This cell could actually be a lot of things, so it could be anything from 2 to 5 from what we know. Although the Renban line might restrict that, because if it was a 2, those would sum to 17, which had to be 8 and 9, and 2, 8 and 9 cannot exist in the Renban line. So shall we actually try going through every possibility? We know 2 didn't work because we said about that just now. 3 would have to be with 16, which is 7 and 9, and 3 can't be with 7 and 9, so 3 doesn't work. 4 has to be with 15, which is either 7, 8 or 6, 9. 4 cannot be with 6 and 9, but 4 can be with 7 and 8 if you used 4, 5, 6, 7, 8. And then 5 has to be with 14, which is, it can't be 5, 9, so it's 6 or 8. And 5, 6, 7, 8, 9 does work, so you can have 6, 8 there. So this could be 4 or 5. If it was 4, we knew it'd have to be 7, 8. If it's 5, we knew it had to be 6, 8. So I guess we could do that, and we know 8 is in there somewhere. So because 8 is there somewhere, even if you had started from 9, you need 9, 8, 7, 6, and 5. So you need 5, 6, 7, 8 on the line somewhere. Yeah, you need 5, 6, 7, and 8 on the line. Although I'm not sure what that does. Okay, what I do know is that this 4 and 5 here mean that either sums to 3 or 4, which means this either has to be a 1-2 pair or a 1-3 pair, with a 1 in one of those cells as I marked. Actually, where the 1 goes would have to be followed by 2 and 3 as well because of the Renban line. Yeah. And really, in reality, all these lines can only be a maximum of 5, right? Because even if you had 3 in here, which is as high as you can go, 3 lines can only be going from 3 to 5. So these digits have a maximum value of 5. Yeah. Not sure if that is useful. But I guess you can say that, I don't know, there's kind of 4 in it. So it's either 1, 2, 3 or 5. But that's a lot of options for the 8. And then the 14 gauge, even if it was a 1, this also has a lot of options. Okay, I want to say that you could do something here as well, but these are all pushing in towards the middle already. This was on the low side. This is going a bit higher. And this is also going a bit higher. So I feel like that is a little bit less of what we want. Because we now know that this has to be fairly low, this has to be a bit higher, which allows them to cross with each other a bit more nicely than this. Oh, I know, wait, hold on. I know that 6 and 7 have to be here, right? Because 8 is here, and either 4 or 5 is here. So you must have 6 and 7 here as well. So should I mark that down? You need 6 and 7 in one of these cells. Your line must have 6 and 7. In fact, your line just must have 5, 6, 7, and 8. And obviously these can't have... Oh, I know. These have to be... These have to be 4 and... no, wait. No, this could be 5 and... Okay. No, this must have a 6 in it. Right, okay, let's think about this. Because this is at least a 4, your line... Could your line have anything less? No, we knew that our line must have an 8 in it. So at the very least, this has to be 4, 5, 6, 7, 8. Which, what that means is that... this must be from the range 4 to 9. And can't be both 4 and 5. Which means the minimum they can be is 4 and 6, which is 10. So this can only be a maximum of 2. So this is either 1 or 2, and we know that because this is at most, at least a 10. And in fact, it really can't be any higher than that, right? Well, no, it could be an 11, which could be made out of 4, 7, or 5, 6. So again, we don't know if this must have a 6 or a 7 in it. We do know if it's 10, it's definitely 4, 6, but if it's 11, it could be either. But that means 9, oh, that means 9 can't be on the line. Right, because 9 we knew are not in those cells. And we know that 9... We know that 9 can't be there, because 9 would have to be accompanied by a 1, 2 pair, and we know those cells are definitely not 1 or 2. So 9 can't be on the line at all, so this just has to be 4, 5, 6, 7, 8. If 9 is not there, it must have an 8 in it. Yeah, it must be 4, 5, 6, 7, 8. So I guess we can mark those down. We can finally remove 6 and 7. And we know those cells are not 8. But yeah, as you can see, once again, there are a lot of options here. I think we can move 8 from here as well. But we do know that this forms a 4, 5, 6, 7, 8 quintuple, which gives us a 1, 2, 3, 9 here. And because this is 14, we can figure out what that digit is. 1, 2, 3, and 9 sum to 15, right? Yeah, it's 6 plus 9 is 15. And because this sums to 14, this is the remaining... I can't say remainder, that's not right. This is the remaining digit to make 15, and has to therefore be a 1. And therefore we know this sums to 11, which again we said has a lot of options, so... Yeah. Alright, but at least there's a digit. We finally have our first digit. So that's awesome. Okay, and we know one of those cells are 1 from our very beginning, which means that in this box, 1 is on the line. Right, because now those cells are 1. So 1 is on the line, which therefore means that this has to be 1, 2, and 3. So that's great, which means 9 is on this part of the line because none of those are 9. So this has to be the 5, 6, 7, 8, and 9. Oh, and that does so much. Because we know now that has to be a 5. Because if it's any bigger, then this has to be summing to 2 or less, which doesn't work at all, because you can't have 1 and 1. So this has to just be 5. This has to therefore be a 1, 2 pair. That's so clean. That is such clean logic. I love that. Alright, 1, 2 here means those are not 2. So 2 in this box has to be there. This has to be 4, 6, 7, and 8. Right, and the only pair that makes up 12 here would be 4 and 8. Because 6 needs to be with 6, which doesn't work. 7 needs to be with 5, which doesn't work. So this now can't be 4 or 8. 6, 7 pair, that's cool. Alright, so... Right, now that actually forms a 6, 7, 8, 9 quadruple, but another thing you could try and say was where does 4 and 5 go in this row? Has to be there, so that forms a 4, 5 pair over there. 6, 7 does form another pair here, so 8 must be there. So none of those cells are 8. Wow, we're just bouncing around, that's awesome. This is now a 3, 4 pair. Those cells have to be... I think they have to be 5, 6, 7, 9 to complete the column and the box. And there you go. I Actually, those cells do give us some options. This could be a lot of things though. Because at the very minimum, if you used 1 and 6 here, you need another 6, which obviously isn't possible. Alright, yeah, so I guess this can't be as high as 6 then. Because if you think about it, yeah, the only way to make 6 is if this was as low as possible, which it can only be made 1, 6. So this can't be 6. It can't be as high as 6. It has to be lower than that. And because if this is 3 or 9, that makes 12. So this is at least a 1, which, you know, by regular Sudoku we can figure out. So this is somewhere from 1 to 5. We know it can't be 5. So this is 1 to 3 or 4. That might not have been as clean as intended, but there you go. Alright, maybe that affects this cell here, which is probably 8 kh. Not sure. But I guess, how high could this really be? It could be 6, right? It could be as high as a 6. Which works with a 2 here. So it could be anywhere from 1 to 6. So that's a lot of options. Alright, well. That is fun. What next? Maybe it is time to look at this then. Or this line over here. Because this gave us some stuff. Not sure if this would give us more stuff though. Or maybe it's this 9 or this 14? Because this means this is at most a 5. But those two can sum to 9 very easily. Alright, fine, let's do the math here. Those sum to 29. So those have to sum to 45 minus that, which is... God forsake, I can't do the math. 45 minus 29 is 16, I think. So those cells sum to 16. And they have to be relatively close, I guess. I mean, that doesn't really give us much. 3 cells with 16 is very in the middle. I mean, let's think about how 16 can be made first. For example, if you use a number as low as 1, right, then at maximum you can have 5, and 145 doesn't give you 16. So it can't have a 1 in it. If it's a 9 also doesn't work. Because 9 will require you to have 5 and 6 minimum, which adds up to what, 20 already? Okay, so it is very middle, and I guess that means it's forced to be quite in the middle by the Renban line. Does something like 2 to 7 work? Sorry, 2 to 6, does that work? 2, 6 actually doesn't work either. Huh. Well, maybe we could try figuring that out. Yeah, could this line have like a oh, no, that's... Could this sum be made of 2, I guess, is what I say. And then 2 would have to be with 5 and 6 maximum, which doesn't work. Then 3 would have to be with 6 and 7, which does work, just barely. 4 would have to be with... 4 would have to be with, or 4 can just work anyhow it wants. It would be like 5, 7, 4, 5, 7 works. So at the very minimum, you can't have 1 or 2. But that doesn't mean your Renban line can't have 1 or 2, because 1 and 2 can be here. Right? And then the 3 remaining cells could be there. Although I'll tell you that 2, 3, 4, 5, 6 actually doesn't work, because even if you use the 4, 5, and 6 here, that adds up to only 15. So your line can't have 1 or 2 in it, that means. Oh, but that means it can't have 8 or 9 in it, can it? If you had 9, the lowest you could go is 5, 6, 7. Which is what? 5, 6, 7 is 18, which doesn't work. Because you need to be at 16 exactly. And 5 to 9 would give you 18 at least. Right, and 4 to 8 would mean, again, the minimum is 4, 5, 6, which works. So your options could be 3 to 6, 3 to 7, or 4 to 8. Basically, I don't know if I want to use that, but if you follow through, I hope you understand that the option here is either 3 to 7, 3 to 6, 3 to 7, 3 to 7, or 4 to 8. Yeah. Okay, that's quite mean. That's quite mean. But I will say that I should have known that, or I should have used the trick. Yeah, this gives us another digit. I should have used the trick that a 5 length Rembrandt line always has a 5 on it. Because if you imagine 1 to 9 as a number line, right? Then wherever you pick out a set of 5, it will always contain a middle digit, which is a 5. And so there must always be a 5 on this Rembrandt line, no matter what. Whether the sum or whatever, it must have a 5 in it. And because of this 5, those can't be 5, which means 5 is in one of those cells. And now we can do the exact same thing here. Those can't be 5, which means 5 is in one of those cells. And that looks at this cell, so that's 4, that's 5. So that gives us a digit. And now those must sum to 4, which can only be made with 1 and 3. So that was probably way easier. Well, now again, I guess now these lines can have 5 in them. Oh, and they can actually have 6 in them. Oh, and they can't have 4 in them. Right, so actually, because they can't have 5 in them, and even if you had a 3 here, you can't go all the way up to 6 on this line. You can't, yeah, you can't exceed 5, you can't have 5, you can't have 4, so you can only reach 3. And the only way to reach 3 in 3 cells is just with 1, 2, and 3. So those are 1, 2, and 3. Whoa. Anyway, so those cells have to be 5, 8, and 9, and that can't be 5. So this does have a 9 on it, which means this must be 9, 8, 7, 6, 5. So that has to be 6, 7. Oh, that was way faster. I just wish I knew I could do that. Oh my goodness. Anyway, this 1, 2, 3 makes that digit either a 7, 6, or 5. That can be a 5, so that can be a 3, which forms a 6, 7 pair. So that's sweet. Okay, I should have definitely used this trick. Not sure how that works here though, because this does not need to have a 6, 7 on it, except that it does. It does. And the way I proved it just now was by saying that this line has to be either 3, 4, 5, 6, 7 or 4, 5, 6, 7, 8. And I'm just going to reiterate as to how I got that. So we know that a box must sum to 45. That is 15, that is 14. So these 3 digits must sum to 16. So how do you make 16? If you had 1 on the line, then you need 1, 2, 3, 4, and 5. The highest you could go is 3, 4, and 5 on these cells, which would only add up to 12. So that doesn't work. If you had 2 on the line, at the maximum you would need 2, 3, 4, 5, and 6. And even if you place the maximum on these lines, 4, 5, and 6, you would only have 15, which is not possible. 3 on the other hand is possible, because 3 could be with 6 and 7 to make 15. You could have, I don't know, 4, 5, 7, that works. And for 4 to 8, that also works. However, you started from the other side, and you said, can 9 be on this line? Well, 9 on this line would give you 5, 6, 7, 8, 9. If you went as low as possible, as to say 5, 6, and 7 are on these cells, that adds up to 18, which is too much. So 9 doesn't work. And we know 8 works, because 8 could be with 4 and 5. Sorry, wait. 8, sorry. With the 8 line here, this could be 4, 5, and 6, which is at least a 15. So those cells could be at least 15 if you have 8 on there. So that works, which means this is either 3, 4, 5, 6, 7 or 4, 5, 6, 7, 8. Right, so it must always have 5, 6, 7 on it. Well, I guess it must always have 4, 5, 6, and 7 on it. So 6 and 7 come in those cells, and because this line must have 6 and 7, those cells have to be 6 and 7. Which looks at that cell and say that has to be a 9. Which just means those cells have to be 4, because this is a 9, that is 13, so that's 4, which has to be made with 1 and 3. This cell is now therefore a 2, because of the 1, 3 pair. And those cells have to be 4, 8, and 9. No, it has to be 4 and 5. They have to have a 4 and 5 in them. Right, and we know now that 1 and 2 cannot be here. Right, okay. 1 and 2 now cannot be on this part of the line. And so 1 and 2 have to be there. And if 1 is there, the line has to contain 1, 2, and 3, because it must contain 3 consecutive digits. So now those digits have to be 4, because it can't have a 3 in it, it has to be 4, 5, 6, 7, 8. So it's 4, 5, and 8. Which means that cell can no longer be 8, that's 9. Alright, that is very scuffed. I hope that was somewhat intentional, but if it's not, I apologize. Okay. So now let's continue on. Those have to be 1 and 2, 1, 2, 3. That is 5, 6, or 7 based on this 1, 2, 3 here. This sums to 9. The 4 here means those have to sum to 5 and can only be made with 2 and 3. So that's cool. Okay, where does 9 go in this box? 9 can't be there because 9 oh my goodness, if you put 9 there, this is already at least 11 if you use 5 and 6. So those digits have to be at least a 20 if you put a 9 here, which doesn't work. So 9 is in the 14 cage and therefore must be accompanied by 2 digits that sum to 5. You can't use 1, 4, so it must be accompanied by 2 and 3. Therefore that places a 1 in there as our last digit, which resolves this 2, 1 pair. That is not 2. Those cells must therefore sum to 14, which we can see is only possible with 6 and 8. Yeah, it's only possible with 6 and 8. 5 here needs a 9. 7 here needs another 7, which just doesn't work. So it has to be 6 and 8 like this, which is resolvable. Okay, that's great. What now? I mean, we have a lot of stuff already, so I guess we just do regular Sudoku, maybe? I think this windmill looks very... Yeah, this windmill is almost completely rotationally symmetrical though. Look at that. But I can't prove that it's symmetrical, even though I want to say that it is. I can't show that. I need to show that. At this point we're down with the biggest Renban lines. We're actually down with all the Renban lines. We know what digits goes on there. So they're not going to be half us anymore. It's really just killer Sudoku at this point. So that's cool. Those digits have to sum to 9. Can't use 1, 2, and 3. So the minimum we can make is 4 and 5, which do sum to 9 exactly. Ah, that makes us an 8, which is interesting because this 8 is not actually rotationally symmetrical with that. So this 8 means those sum to 4, which is only possible 1 and 3. That removes 3 from those cells, which makes this a 9. That's a 2, so that's 3. Which resolves the 3, 4 pair. Okay, cool. That digit is now a 6 to complete the column. Those digits have to be 7, 8, 9 to complete the box. Those digits have to be 2 and 4, which we can resolve to complete the box and the column. Cool. 6, 7 pair here means what? Well, this 1 resolves this 1, 3 pair first. 3 resolves this 3, 9 pair. which does give us a bunch of stuff here. Oh, another 3 in the corner. Did we have that last puzzle? I think we did. 6, 7 pair here means those digits have to be what's remaining, which are I think 4 and 8. Those digits are 4, 5, sorry, no, 5, 6, 7 and 9. 7. So we could probably do something with the... Well, this 14 cage first, I guess. This 9 here means those have to sum to 5 and can only be done using 2 and 3. This 2, 3 pair means that is now a 1. And we get a chocolate teapot here, so that's sweet. I guess we do look at this then. 4 here needs to be with 7, 9, which is possible, I think. Yeah, 4 can be with 7, 9 to make 20. 8 can be with 5, 7. I guess it means 6 can't be there then. Right? I don't know. If 6 was here... If 6 was here, the remaining digit have to sum to 14, which isn't possible. Because the 8... The 8 would need another 6 and the 4 would need a 10. Yeah, so I guess 6 isn't possible there. And I think you need a 7, right? If it was 4, it needs to be a 7, 9. If it's 8, it has to be 5 and 7. So 7 is one of those cells, which does help us resolve this thing. This now has to be 6. Here, 7 there. Those now can't have 6 in it. Actually, that can't have a 7 in it because we know 7 is one of those cells. This 6 means that has to be a 2, which resolves this entire thing here. That resolves this entire thing. That must therefore be a 7, which gives us a 7 here. Great. 7 resolves the 6, 7 pair. Those digits have to be 4 and 5, which we haven't resolved yet. Those digits have to be 2, 3, 4, 5, no, 6, 7 and 8. Sorry, no, 6, 8 and 9. That can't be 6. Those digits sum to 18. Ah, so it must have a 6. These must have a 6 in them. Without it, it will be 8 and 9, which sum to 17. This cannot be a 1 to make it 18. So 6 must be in here somewhere, and definitely can't be there. So 6 is there. And now 6. If 6 was with 8, it would need to be with 4. If 6 was with 9, it would need to be with 3. Oh, so this doesn't work. Well, I mean, it does work, but it only has one option, which is 8 and 4. If this was 6 with 9, this would need to be 3, which doesn't work. So we can do that. Resolve this entire thing, which should resolve everything upstairs. That has to be 8. That's 4. This 5 means that's 9. That's 5. And we have this little plus sign over here, which might help. Those digits are 3, 4, and 9. Yeah, and let's do one final trick. Those digits sum to 16, and because those sum to 16, this sums to 25. Those digits have to sum to 9, which cannot use 2, 7, 1, 8, or 3, 6 because 3 is already in the box. So they have to be... Wait. Sorry, no, 16 is with... Yeah, 16 is with 9 on this one. How do you make 9? Wait a minute. How do you make 9? Did I do this wrong? You can't make 9, right? Wait, does this not under 15? Wait, is it not 16? This is 16. Wait a minute. I did something wrong here. Yeah, I definitely did something wrong. Because there's no way to make 9 in those cells. So, I mean, I'm just gonna look at the list here. Yeah, 3, 4, and 9 has to be accompanied by either 1, 8 or 2, 7, which isn't possible. So I did something wrong here. Yikes. Did I do something wrong? Oh my goodness, where do I even... Wait a minute, hold on, I gotta check if I did my math right here. Does it sum to 20? It does sum to 20. I did my math very, very wrong. Does this sum to 18? Wait, this isn't even something. Oh, I'm so dumb. Alright, this is wrong because for this to be 18, this is 8, that has to be 4. Whoopsies. That's 5, so that's 9. And hopefully this 4 resolves this 4-8 pair differently. That this 5-9 pair actually still remains unresolved, although we can do that with this 20 cage. This 4 and this 7 means that has to be 9, so that's 5, which gives us different digits. Yay! This has to be 3, 4, and 5 now. Thank God. It wasn't like a huge mistake at the very back. So those have to sum to 13. You can't use 5, 8, or 4, 9 because of the 4, 5 there, so this has to be 6 and 7. So this can no longer be 6 or 7. That can no longer be 7, giving us a 4, 5, 8, 9 quadruple here. 1. Well, these have to be 1, 2, 8, 9, right? Those cells can't be 1 or 8, and those cells can't be 2 or 9, which gives us some very interesting. Oh, right, it's this one, because this 3 here means that has to be 2, 3. This 3 means that's 1, this 1 means that's 3. This 1 resolves this 8-1 pair. This 2 resolves this 2-9 pair. Yeah, and I think we're on our way. This now can't be 3. And then a bunch of stuff happens. 8 can only be there. Yeah, so 8 has to be there. That's 9, that's 7. And then I guess this 3 can't be there either. I don't know how I missed that. So 3 goes in the middle. So now 8 here makes that a 4. That's an 8. 4 means that's 5. That's 4. This is 9. And then we are basically done, I hope. Yeah, this digit has to be a 6 to give you 12, which resolves this almost deadly pattern. This 6-7 pair is resolvable. This 4-5 pair is resolvable, giving us solved in 34 minutes and 4 seconds. Yeah. This was very fun. I don't know about this line. I really hope I got it right by looking at this line and finding its options. I feel like that is not very clean. It's not really how full deck and missing a few cards would do their puzzles. But yeah, it's still a very enjoyable puzzle. I hope you enjoyed that too. I'll see you next time. Bye bye. Hello. This is Low Places by James Sinclair from his Artisanal Sudoku Volume 108. We got a interesting little line over here, so let's get right into the rules. Normal Sudoku rules apply, so place the digits 1 to 9 in every row, every column, and every 3x3 box. Digits on arrows sum to the number in the connected circle, so for example, those 2 digits sum to that digit, those 3 digits sum to that digit, and may repeat if allowed by other rules, so those digits could both be 2, making a 4 there. So those are the arrows. We also have this little small circle here, which is a quad rule, quad clue. A digit inside a white circle must appear in the one of the 4 cells surrounding that circle. So 1, 3, 6, and 9 are in these cells somewhere. And finally, the long orange line. Every set of 3 adjacent cells must contain 1 low digit, 1 middle digit, and 1 high digit. So those 3 cells, for example, must contain 1 low digit, that is a digit from 1 to 3, a middle digit, which is from 4 to 6, and a high digit, which is from 7 to 9. And this line is actually called an entropy line. Yeah. So yeah, interesting new rule. I don't think I've ever seen or went into much detail about this line, this type of line before. So I'll be excited to try this out. Let us begin solving. So, okay, well, what I can tell you about this line is that because any 3 set of adjacent cells must have 1 low, 1 high, 1 middle, it forms sort of this looping pattern, right? Where this one has to be of the same type as this one. They have to be both high because those two are, you know, if this is high, then this is middle and low. And because this is middle and low, these 3 have to contain a full set, so that has to be high. And basically you kind of get this looping pattern where every 3rd cell is of the same type. I don't know what it's officially called, but yeah, those 3 cells are of the same type. And actually, this actually does seem to be a pretty high type of clue, because I can mark, well, I mean, because we don't actually know which type this is, we know these are all the same type, I will mark them as a certain color, and I will do the same for all the other sets here. Those are the same type, and those are the same type. And theoretically, or not theoretically, but the standard that I use for this line is that blues are lows, yellows are middle, and reds are highs, but we don't know, so we're just gonna leave it here for now. We do not know that this is 1, 3, 6, and 9. So what that means is that here we actually have 2, 4, 2, 4, 2, 4, oh my goodness, 2, 4, 5, 7, 8, which actually does seem very interesting, because that actually, oh wow, wait, that is very interesting. Right, this actually gives us a lot. So this cell here is the only type in this box. Therefore, it must be, you know, on its own. Those two have to be the same type, and those two have to be the same type. However, we know that those two then can't be from, they can't have 2 in them, because 2 is the only one in the low type. This one also can't have 2 in them, because 2 is the only low in these 5 cells. Which actually means that this is where 2 goes. Yeah, I should explain that more properly. And I guess the way I would explain it is that if you put 2 in one of those cells, you can't put another low digit in the opposite cell, and same for the yellows. So 2 has to go there, which is super intriguing, because that we thought this was a high digit, which is actually not. It's actually not a high digit. So we know now that all reds are low digits, which gives us a lot, because a lot of these are actually on the arrows themselves. This 2, for example, can only be made with 1 and 1, so those must just be 1s. This must therefore be 3, which means that's 3, because those two have to be the same digit. This, well, this can't be 1, because these two digits are both at least 1, so this can't be 1, it has to be 3, it can't be 2 either. That can't be 3, that can't be 3. And in fact, this 3 means those two form a 1-2 pair. This 3 means those two actually form a 1-2 pair as well, because that's the only way you can make 3 in 2 digits. So this has to be 1, that has to be 2. Wow, okay. That's also 3. Right, I think this one has to be a 3, because those are 2 different digits. So the minimum this can be is 1 and 2, which sum to 3. So that's 3, these form a 1-2 pair. And I guess we now know, therefore, that these actually are low digits. Yeah, and actually the low digits, I think I'll just mark as blue instead. So those are blue, and then all the blues. Oh, see, I confused myself here. What am I doing? Low, low, so yeah, I confused myself. Hold on. Wait, oh, I colored it wrong. Okay, hold on. Oh my goodness, I colored all these wrong. The blue, the reds are right. The reds are right. And in fact, all the reds I will now mark as blue in color, because that is the standard for low digits. These are the same type, which are going to be something, and those are the same type, which are also going to be something, which are that. So there you go. The colors are more accurate now. Okay, 3 in this box here must be there, because 3 can't be in that cell. Those cells can't be 1 and 2, because 1 and 2 are already there. So 3 has to be there. So this digit is now at least a 4, so that digit is at least 7. And I guess we know that because of those 3 digits. If you place the minimum 1, 2, and 3 there, you would get a 6 at minimum. But we now know this is at least 7 rather than at least 6. This one could still be at least 6, I think. If you put a 3 here and a 1-2 pair there. This 2 does fix that though, so this is 1, 2, 1. This 2 means that's 1, that's 2. Ah, and all 3 of these 1s do help with those digits, because those digits now cannot be 1. So the minimum they can be are 2, 3, and 4, which add up to 9. So that's 9. These have to be 2, 3, 4. The 3 see those cells, so 3 goes there, forming a 2, 4 pair here. Sweet. 1 in this column cannot be in those cells or those cells, so 1 must be there. Actually, this 1 also sees that cell, so 1 goes there, and therefore this must be an 8 to give you 9. I don't know if I want to continue coloring the rest of these digits until we get more information. I can color those digits in as blue though, not sure if I want to. But now we have 4, 5, 6, and 7. Right, therefore I can say that those digits have to be the middle, which means my coloring was right. Because there are only 3 of each type in every set of 1 to 9, right? And we know those 2 are high, so those 2 cannot be both high, because then you'd have 4 high digits in here, which doesn't work. So these can't be high, they have to be middle digits, which are 4, 5, and 6. So those are therefore high digits, which means the last high digit here has to be a 7. That is also a middle digit to complete the column. So we now know that all those digits have to be fairly large, they have to be on the high side. Those digits are middle, so those are 4 and 5. Those digits are high, so they are 7 and 8. Great, a lot of progress already. This 7 means that's 8. 8, so that's 7, that is no longer 8. And I guess I can mark these as 4, 5 as well. Maybe we could do this though, because this contains 1 middle and 1 high digit by the row here, and the high digit is always higher than the middle digit, so this one has to be lower than that, so that is always a high digit, which I guess you could also know from the fact that it's either 7, 8, or 9. So this is 4, 5, or 6, which unfortunately does pair up with that very well, so any of those options will work. What about 1s? Well, could this still be 2, 3, 4? It can't, so it must have a 1 in it. There you go. Because of all these 3s, this cannot be 2, 3, and 4. And if you didn't have 1 or 3, the minimum you could have is 2, 3, and 5, which is 11, which doesn't work. So this cannot have a 3, therefore must have a 1 in it. 1 can't be there or there, so 1 goes there, which must be accompanied by some stuff. It could be 2 and 4 at least, which does give you 7. So once again, this is fine. Yeah. Actually, I don't think this can be 8 then. Well, no, it could be 8 if it's 1, 2, 5, right? Yeah. Okay. This digit? I mean, that digit cannot be low anymore. So it's either middle or high, but it could be high, couldn't it? It could be 7 with 9 here. 7, 9, and then a 2 there. Yeah. In fact, 2 is in one of those cells, which means it's probable that 2 goes here. I guess it's not probable, it's more like something. Well, okay, where does 8 go in this box? 8 can't go on this line, because even if it had a 9 here, 8 can't merge with 1, you know, 1 is already there. 8 can't be there either, because that forces this arrow to be more than 10, or 10 or more. So 8 is in one of these 3 cells. Weird, but sure. I feel like we could do a lot more with this. Yeah, definitely feels like we could do a lot more with this. Shall we finish up the 1s? I think we can put the last one. Yeah, 1 goes there. It just is there, so that's all the 1s, I think. Cool. We could maybe try the 3s as well. Yeah, those can't be 3s anymore, so 3 goes there. And then I guess, whoa, 3 in this box? Yeah, 3 in this box has to be there. And then, is that all the 3s? Yes, that's all the 3s, okay. What were the 2s? 2s are a little bit weirder, because, yeah, they don't have a lot of options. 2 is in one of those cells. And 2 is in one of those 3 cells now. I don't know if we can eliminate 2 from being here. Maybe you could with like some big brain math with this, but I don't think I can see it right now. Alright. Moving on. 8. No. I mean, this is sort of close to just regular Sudoku at this point, right? We only have this one and this one to worry about. We know that is, well, because of the 2 here, we know that that's already at least a middle digit. This could be 2 though, so this could be 5. So I guess this is, well, these digits are all 5, 6, 7, and 8. Which I don't know if I feel like marking, but I guess I will. So because that's 5, 6, 7, 8, this has to be 2, 3, 4, 5. But we know this can't be 3, so that cannot be 6. Is that the only thing? Yeah, that's the only thing then. Yeah, the 5 and the 2 here are the only things stopping us from defining the colors of those cells. I mean, what are we missing from here? We're missing a 9, which could go anywhere there. Yeah. Okay. What else can we... 2 is in one of those cells. But in here is in one of those 3 cells, and in here I assume it's in it's in any of those 4 cells. I don't know. We might have to delve into some coloring here, because I can tell that this is 1 middle and 1 high, and this is 1 middle and 2 highs. Actually, those are also 1 middle and 1 high. Is that useful? Don't know. I mean, maybe it is. We know that's 1 middle, 1 high from the 6 and 9. Nice. Anyway, what am I talking about? What's something I'm not seeing here? Maybe that doesn't... Maybe that's constrained somehow. I mean, if it was 7, how would that work? If it was 7, you could have... You'd need to have 4 there, right? A 7 here would require a 4 there. This would therefore have to be a 1, 2, 4. Because this can't be 4, that's 2, and then that's 4. And that'll be 5, but that's fine. Actually, yeah, those digits are all very constrained, right? They're all different, and they sum to those 2 digits. So at maximum, those digits are 8 and 9 in total, which is 17. I mean, 17 is still a lot, but I guess we now know that that can be 5 then, right? Because those digits are at a minimum 1, 2, 3, 4, and 5, which sum to 15. Those digits therefore have to sum to at least 15, but if this was 5, then this would have to be at least 10, which doesn't work. So this can't be 5, that can't be 2, which does mean we have confined those to specific colors as well, which might be helpful. But I guess these can't both be 7. What does that mean? If one of them was 7, the other one have to be... Oh, if this was 7, that has to be 8. Could they both be 8? Yeah, they could both be 8. Although I don't think they could both be 8, could they? They can't both be 8, because those would have to... Yeah, it's very hard to explain, but if they were both 8, then this sums to 16, which is only made with 1, 2, 3, 4, and 6. However, if these were both 8, that would be a 5, which isn't in the set 1, 2, 3, 4, 6. So they can't be both 8. I don't know how useful that is. I'm inclined to say that it has to be 9, but I also can't prove that. If this was 7, then this would be 8. But 3, 5 with 1, 2, 4 does work here. Oh wait. I think 7 here does it work? No, it doesn't, does it? It doesn't. 7 here doesn't work. Alright. Because 7 here would force this to be a 4. Will force that to be a 2, because there's a 1, 2, 4 and this can't be 4. And here you have 1, 2, 3 and 4. But how do you make 7 in 2 cells like that without using 1, 2, 3 and 4? You can't use 1, 6, 2, 5 or 3, 4, and therefore you have no options for this arrow here. So this actually can't be a 7, which is interesting. I think 8 might be similar. 8 here makes that a 5. This has to be... Well, hold on. If this was 8, then this is 5. Those have to sum to 7, which could be 4. Well, no, we know that doesn't have a 3 on it because of these 3s over here. So if it was 8, how would you make this without using a 3? You have a 1. The remaining digits need to add to 7 without a 3 or a 1 on them, which would have to be 2, 6. Wait, no, which would have to be 2, 5, sorry. Right, so 8 needs to be with 2 and 5. So this 8 puts a 5 there because of the 3. So this can't be 5, that has to be 2. 5 here, and that doesn't work again. Right, wow, okay, very interesting. This 8 here puts a 5 there because it was sum to 8. This, to make 8 in 3 cells, you can only use 1, 2, and 5 because you can't use 3 anymore. But since 5 is here, that would have to be 2. And now you have 1, 2, and 3 all in the same box. So how would you make 8? You can't use 1, 7, 2, 6, or 3, 5. So once again, there are no options. So this has to be 9. And I wonder if there's a more simple way of explaining it. There might be, actually. Yeah, if you sum up all those cells together, there might be an easy way of explaining it. Yeah, I don't know. See those digits? Yeah, I think that trick could eliminate 7, but it wouldn't eliminate 8. It wouldn't eliminate 8, but it would eliminate 7. And the reason to say that is because those digits are all different. They therefore have to be at least 1 to 6, which sum to 21. This is at least 2 then. Yeah, this is at least 2 because it can't be 1. So those digits are at least 24, and because there's 3 sets that sum to this digit, this is at least an 8. Right, so by that logic, you can eliminate 7 from here. Was eliminating 8 correct? Did I do my logic right? If this is 8, the way you have to go with the minimum, making that a 2, making that a 5, making that a 5, which doesn't work. Right, so 8 also doesn't work because that will force 5s in both of those cells. Yeah, 8 here would mean we would need this to be absolutely a minimum. That would need to be 2, that would need to be 5, that would need to be 5, which doesn't work. So this has to be 9. So that is 6. 6. That's 7, that's 8. I'm not very happy with the logic that I did with this 8 over here, but if it works, it kind of works, I guess. Right, so now we know those have to sum to 8. They can't use 3, 5, because you can't have 3. They can't use 1, 7. They can't be... Yeah, therefore they have to be 2, 6, because they can't be 4, 4. So this can't be 6, so that's 2. That's 6, and we know that that has to be 2 then. So this now can't be 6. 6 has to be one of those cells in this box. Wait, no. Yeah, because 6 can't be there. So this is so 6 in this row has to be here then, which resolves the 6-9 pair. While this 6 also did that. So those digits are now 4 and 5, which means that digit is 6. That digit is 8 or 9. And and we'll do the coloring when we're done. But those digits now sum to 9. They can't use 1, 8, 2, 7 or 3, 6, so they have to be 4 and 5. So the remaining digits there are 7 and 8, which we can't resolve, but that does form a 7-8 pair here. Because this doesn't use 4 or 5, this actually could still be either. So that's weird. Alright. We should be able to do more from here. Like, where does 2 go in this box? Because of these 2s here, none of those are 2s, that's not 2, so 2 goes there. So the 2 is not there, meaning 2 in this box has to be here, which resolves this 2-4 pair, which resolves the 4-5 pair, which doesn't do anything to this 4-5 pair, but it puts 5 in one of those cells. This is also a 4-5 pair, so the remaining digits in this column have to be 7, 8, and 9. Those digits can't be 7, so 7 goes there. Actually, that digit is 4, 5, or 6 as well. Whoa, 4, 5, or 6, which forms a very interesting little triple here. And so the remaining digits have to be 7, 8, or 9. This can't be 8, so that's 7 or 9, which are high digits. Maybe I'll start coloring those in right now. Those are high. Those are medium digits. Medium. Those will be high digits, and all the 2s have to be low digits, which gives us all our low digits, I think, except the 2 in this box. The 2 in this box has to be there by regular Sudoku. Yeah, that gives us all the 2s. Cool. So now this 8 resolves this 8-9 pair, which does what? Probably does more stuff. Those 2 digits have to be 6 and 7, which we can resolve by this 7 over here. Those digits are now 5 and 7, which we can also resolve, which resolves this 7, 9. Well, it resolves this chocolate teapot here, which I did not actually mention this time. Funny enough, I did not mention that there was a chocolate teapot there. That's not 7. That is 6 to finish the row. Great. I think we should remove those colors, because we could probably do regular Sudoku with them now. 6 means that's not 6, so 6 in this box must be there, which we could have done by Sudoku, which we did do by Sudoku, so that's funny. This 6 removes 6 from that cell, so 6 must be there, which gives us all our 6s. Great. 5, 7, 8 triple here removes 5 from there, so that's 4, which means this has to be 7. Those are no longer 7. That has to be, I think, has to be a 9. So 9 in this box has to be there. Those digits are 4, 5, and 8. This can't be 8 or 5 by those digits, so that's 4. This 5, 8 pair is resolvable. Resolves this 4, 5 pair here, which fixes the rest of the 4, 5 pairs here. Cool. We love a cascade. We love a good cascade. These are 5 and 9, which are resolvable, which resolves this 5, 8 pair, which means we're almost done. So before we're done, let's start. Actually, I'll put the last 2 digits in first. That digit has to be, well, these 3 digits are 4, 7, and 8. That's 8, that is 4, and this will be 7. So before we're done, let's just color everything in first. All the 7s to 9s are high digits. All the 4s, 5s, and 6s are low digits, and the 4, 5s, and 6s are middle digits. This has to be 7. Solving it. Oh my goodness. Okay, 7's here. There you go. 24, 42. Yeah, that was cool. I really liked it. Very interesting start. I never expected this to be a low digit. Hope you enjoyed that puzzle. I'm off now. Bye bye.